Hello, everybody. Great to see you, everybody. My name is Hwang, who is leading the AI R&D and MX division of Samsung Electronics. Today, before going to the presentation, it's my great honor to have an opportunity to have a great presentation here today. So during the presentation, I might introduce the AI technology a little bit, and I'll show you the examples around the AI, mobile, as well as the healthcare industry. And also, I'll talk around what's the challenges in front of us to make it happen, more future healthcare in our daily lives. This presentation shows the buzzword, word cloud. It presents the AI trend nowadays. The bigger means the more popular, right? So most people already knows generative AI is the most popular word nowadays. And also, in the right side of the corner, you might see the AGI. It represented the artificial general intelligence, which could be almost the human level intelligence with the AI. So nowadays, many people begin to think that AGI could be realized in the near future. So that's why the other terms like ethics or security or the safety around the generative AI should be considered. For this presentation, I prepared this presentation with the generative AI. I want to share my experience with the generative AI. So when I got a request from our contact point, I just got the request just to saying the common AI as a keynote. So I used my prompt to generate the title quite much, like to just put I'm preparing a seminar on the AI general content and role and medical field. Write the title for this. Then generative AI gave the title like this one, Advancing Healthcare Through Artificial Intelligence, a comprehensive overview. It's too common, so I want to revise it. So I put another word to revise. I want to future and innovation to be in the title. Then generative AI, again, gave me the 3 candidates, which could be very good title. So the third one is I think the third one is the best, so just I selected. As a presentation speaker, one of the most difficult thing is to prepare the title quite well, to make it more personative way. So it just took around 5 minutes to generate. If I made the title by myself, it may take an hour to think and to revise it, right? So like this, everybody could utilize the AI quite well in daily lives to do your work or to enjoy it or to another thing like healthcare. So I'd like to mention more about the current AI, and I'll touch the application. So basically, AI designed to replicate the human intelligence. So at the beginning, intelligence started to demonstrate the human perception first, like understanding the visual and understanding the voice and all the information from the environment. Nowadays, as generative AI is boomed, AI started to make a plan or make a reasoning or even created the new content by itself, right? In this AI, 3 components is essential to be built. We called it ABC. First one is algorithm. it mimics the human brain mechanism to think. So we called it as a neural network. And another area is big data, to make AI trained with the data, to see all the cases and possible cases, to combine and to analyze hidden factors. And another component is computing. To make the huge size of the neural network, we have to build the computing environment to see, to train all the big data we collected. That's the three components we have to think. So after having three components quite well, as you most people remember, in 2016, we were so shocked with the AlphaGo. If it's the most intelligent Go player is at all, so we were shocked because it exceeded the human capability with the machine, right? So at the time, we believed that AI is not the future technology. We started to embed it into our daily lives. So nowadays, if you drive your car, you might get a parking assistant or adaptive cruise control to do the more easy driving experience within your car. Also, there are a lot of voice assistants to control at once with your utterance, like a Bixby or Siri in the market. All these things is implemented with the very good AI right now, so you can enhance your daily lives with this kind of AI. So, in the middle of the 1950s, the AI terminology was suggested. Before the 2000s, mainly the AI research is focused on to build the expert knowledge to handle the specific situation in the specific domain. But as you probably guess, it's not robust. It can handle the specific situation, but if the case is just beyond the specific case, it could not handle. So after the 2000, there are two components like big data and computing was established quite much with the internet technology. With the internet, many people started to use it, and naturally, all the data could be gathered in the internet. So big data could be ready, and also with the advanced network technology, server could be connected quite naturally, quite seamlessly to provide all the resources together to make AI trained. So in the middle of the 2010s, third generation of the AI was formed, like AlphaGo and all other deep learning algorithms. Nowadays, it's getting bigger and bigger, including the big data and computing resources. Fourth generation happened. So nowadays, many people mention that the generative AI is another level of another era of the AI right now. So third generation algorithm is mainly on the classification model, and current AI model is more about the generative model. The basic algorithm around the two areas are quite different. That's why I want to explain what's the difference between them. So mainly classification model classifies the input into the predefined classes. So it's quite easy to make AI trained to figure out what's the different features between two classes, among classes. And also, but the generative model, it learns behind the data distribution and data patterns when you make it learn with the big data. And size-wise, below there are a bunch of algorithms which is popular in the market. So basically, classification model is surrounded with hundreds of million parameters. By the way, parameters, you could understand them parameters as the number of synapses in the brain. So in the brain, 100 trillion synapses are there. So you can see that classification model is almost a million x less than the human brain. But in the generative model, it's getting quite huge. It's almost 1,000x than classification model, but it's still beyond the human brain. It means that still there is a potential with the generative AI. We have to think that to make it more robust with the human brain, we need more time to make it happen. And also regarding the training process, it's quite challenging to train AI be accurate in a specific domain or specific tasks. So classification model, it classifies the image into the specific class like a dog or the cat or something else. To make it trained, we have to collect the data and label it manually. It means that it's so human intensive. So it's quite difficult to make it happen quite well because of that reason. Human takes time. It means that it's not so scalable in this case. But in generative model, they run the data as it is. It means that in case of the LMM runs all the passages, all the sentences to predict the next sentence or next word. Naturally, without any labeled data, what is the wrong and what is the fact, we can learn quite naturally. It means that in a generative model era, model could learn the huge amount of the data quite naturally, like all the web data. That's why it's quite easy to make AI model trained about all the data-wise. So for a long time, Samsung Electronics applied a lot of AI algorithm into the devices. Most of all, like a TV, we used the AI algorithm to give a natural screen to the users, not just to decoding the signal from the internet or the broadcaster. And also, we utilize the camera thing to enhance the camera experience to the users with the AI. Also, we want people to be released from the house shopping with a digital appliance, like to find the object you want to do the laundry or you want to clean up. So that's the way we are thinking to give a good experience with our device to the users right now. So recently, we launched the Galaxy AI, which could be the next version of the phone right now. So I'm excited to introduce some features on that. So first one is the translate. It's around the barrier-free communication around the world. Because of the language barrier, many people have some difficulty to communicate quite well. So live translation could provide you to communicate with your foreign friend in your mother tongue. And also you can use the translator over the many tasks like a voice recorder or a browser. Even in the channel, you might use it quite naturally. And also during your travel in abroad, you can utilize the interpreter to communicate with the foreigners quite naturally in real time. And also there is another case. It's about the productivity. So we want to enhance the productivity for the people with the summary and styling. So on the left side of the corner, you might see that all the records could be dictated quite well, and also it will dictate who's speaking in a specific area. And also it could be summarized quite well. And also over the browsing, you might want to check the basic theme or all the important thing quite quickly. You can utilize a summarization technology with the AI. And also, during the documenting, you might want to change the format or you might do some other work, styling changing. In that case, you might utilize another AI functionality in that case. And final one is about the image. So when you take a picture, you might get a picture with an unwanted object sometimes, or the position is a little bit behind your expectation, right? So in that case, you can click the object and remove it or move it and relocation it quite naturally. And then Galaxy will give you the very natural image again. And also we provide the wallpaper, which could be aligned to your date or weather quite naturally. So with the scene, just your wallpaper, you might check the weather and time quite natural way. So if it snows, it will show you the snow picture. And also with your prompting, changing the prompting, you might build your own wallpaper and use it as a personalized mobile phone. This kind of generative AI is designed for your own purpose. So from now on, I want to go more beyond the healthcare area. So I want to emphasize the two enablers. First one is the generative AI model, like language model or vision model. In Samsung Electronics, there is a generative AI model, Gauss. So Gauss has three types of the functionality. First one is the large language model. It communicates with the users very natural way, and it could have some functionality like to change all the sentences and like command or writing a draft mail. And also there is an image model to change or to generate your editing quite naturally. And also there is a code model which can help software engineer to compose the code quite safely and quite quickly. Another enabler, I could say that on-device AI. Everybody might know, right? So on-device AI means that AI learns on device quite fully. In that case, we don't need to send the user data to process it in cloud. It means that privacy protection could be happen. And also, without the connection, it works. It means that the reliable AI could be provided with the on-device AI. And also, it could utilize the personal information on device quite deeply. And also, it doesn't need to send contact to the cloud service. Fast response could be possible. And also, as an AI provider, AI operation cost could be lower than the cloud service. That's the benefit for the on-device AI. That's why, as a device vendor, Samsung Electronics is working on on-device AI. I want to emphasize one more thing regarding the on-device AI. To realize the on-device AI quite deeply, we need a specialized hardware like a neural processing unit. For the visual AI, you might check that the acceleration emphasized on the left side of the slide. So NPU is more powerful, almost 20x rather than the CPU right now. Samsung Electronics, we designed the on-device AI, which could be learned on device fully we improved it almost 40% year by year. And finally, we successfully embedded the on-device large language model on top of it. To make you understand what's MPU performance, I want to find out the actual case which could be comparable to the processing power. It's not an apple-to-apple comparison, but you might check that the numbers only. So in 2000, there is a supercomputer, IBM ASCI. The operation is around the 12 teraflopsing operation per second. But in S24, our MPU could operate over the 45 tera operation per second. It means that if you have Galaxy devices, you bring the supercomputer, 2000 supercomputer in your hand. It's so powerful, and previously in 2000, it was used to analyze a nuclear or weather or very deep problem, right? So that's why we can utilize the AI on device quite well nowadays. So when OpenAI, they announced the ChatGPT, it was a little bit shocked in the healthcare area also, right? These articles shows the news around the ChatGPT could pass the exam, U.S. doctoral exam, right? So without any tuning or without any learning around the medical area, it could pass it. It means that it has the potential to provide the more natural knowledge to the healthcare industry. Even it has the risk to hallucinate or to give an answer very factual way. We don't know quite well about it. So that's why in this event, we expected some instrumental system should be designed. In this picture, you might see a lot of use cases. People coming to the seat, we looked around all the booths to show the actual use cases. From the image synthesis, drug discovery, and personal medicine, and data analysis, even to preparation for the pandemic, we have to think to leverage the AI in the healthcare area. I might give you the more detailed examples in Samsung Electronics, more about this. So first one is about the Samsung Health. Samsung Health is one of the applications you could use in Galaxy phone. So this Samsung Health experience could be provided across our whole devices quite well. So if you are an exerciser, it tracks your exercise habit as well as the nutrition thing. And also, it could track your sleep habit and give you some comment on that. And also, it could monitor your health status with like blood pressure or ECG, even IHRN. It will monitor you and alert you if it is so dangerous. In detail, with the many devices, we provide those kind of AI on top of that. So with the watch, this tracks your exercise and then make the personalized HR zone to change the intensity to make it more efficient exercise. Also, it could track your sleep habit when you go to sleep, when you wake up. All this kind of monitoring is happening with the AI right now. And also, beyond the sensor, it's quite difficult to make it accurate monitor without AI. So we want to make it improved quite much with very sophisticated way. Another area is to provide the actual medical device to the people. So there are 3 examples. So ultrasonic system, digital radiography, and computed tomography. All these machines could be leveraged the visual AI as well as the or generative AI. So in detail, I might show you all the pictures. So on-device chest CAD, you might see the lesion area quite much with the AI. And also, auto-collimation, it adjusts the position quite automatically with detecting all the positions with the AI. And also, chest PA, bone suppression could be done. It means that beyond the bone, it's quite difficult to make it clear what's wrong inside it, what's wrong beyond the bone, right? In that case, we can utilize the image AI to show the beyond the scene. And also live breast monitors the lesion in your breast, and also nerve track will track where the nerve is. And also heart assist will detect the area, all the things with the AI. This kind of AI is just the glimpse of all the possibility. So I want to close with my remark. I want to mention about the 2 things. As I already mentioned, in the healthcare area, most AI algorithms should be more accurate and more reliable. It means that we need more data to be trained with the actual AI model. Because healthcare area data is all about the private data, mostly, right? So we have to think how to boost the collection and how to boost the share about all the possible data which could be used for the AI model. And also, in the future, definitely all AI will be deeply inside our daily lives. But still, in the generative AI, it's not deterministic yet. It means that we don't know all the possible results from there. So ethic problem and safety problem should be addressed. So during this event, I believe that you might get an insight and other people to discuss more around this one. Yeah, that's all my presentation. Thank you for listening.
Thank you very much. As we continue to ask ourselves what GenAI means for the healthcare industry, as employees in the workforce, as engineers, as educators, as regulators, I'm happy to share that there is another industry that has already embraced GenAI wholeheartedly and provides lessons both promising and warning that are directly applicable to healthcare, and that is the video games industry. Most countries, when I say that, I get a confused look or a laugh, but here in Korea, I get a lot of head nods. When we talk about using the video games industry as the guide for what the future looks like. So, I've only been in this country for 3 hours, I already feel at home. The video games industry provides a useful model of how to both approach and leverage GenAI. You can turn the audio off. I don't have any audio in mine. Turn this volume down. Thank you. Great. Instead of viewing GenAI as a threat, the video games industry, our artists, our engineers overwhelmingly view it as a healthy and welcome evolution of decades of innovation. Putting fear aside, the video games industry is using generative AI in ways that are directly applicable in healthcare, in medtech, and in the life sciences, both in terms of how we train AI as well as the problems that we use it for. So a little bit about me. I live at the intersection of video games and healthcare. I run a company called LevelX that uses video game technology to accelerate the adoption curve of new products in healthcare. We have about 1 million medical professionals that are playing our games on their phones, literally earning continuing medical education credit while they renew their medical licenses. We're working with major pharmaceutical companies like Novartis, Amgen, Novo Nordisk. We work with major medical device companies like Medtronic and Philips to help them sell, market, and train on their products. But to be very clear, I don't actually sell any AI products. I make video games for doctors. So this is not a sales pitch for generative AI products. However, at LevelX, we have been heavily using generative AI, just like the entire games industry, and we have been learning lessons that are broadly applicable across all of healthcare, and I'm here to share them. So a little bit about me. My background before LevelX is in the video games industry. I used to work at companies like LucasArts, making Star Wars games. I used to run the DirectX graphics team at Microsoft that was responsible for making video game graphics look amazing. And while most industries are approaching generative AI with fear and trepidation, the games industry is really proving to be an exemplar of the adoption of generative AI. Why is that? I'll show you. You can feel free to cheer for any video games that you've played. In fact, in the last talk, we heard about Moore's Law, right? So the video games industry has been taking advantage of Moore's Law. This is the best-looking video game character we had in 1989, and we just grabbed onto that Moore's Law curve, and we wouldn't let go. This is what the best video game character looked like when I joined Microsoft in 2001, and my team's job was to figure out how to go from this to this. So this is Call of Duty. Today, I can zoom into the face of any of the dozen soldiers on screen in the game, and this is what it looks like. This is the level of detail that we're creating video game characters at in modern video games. Because thanks to Moore's Law, every 5 years, video game hardware supports an order of magnitude more content at an order of magnitude higher detail, which creates a huge problem. The game's price doesn't change. So the only solution for us is to make our employees, our artists, our engineers, 100 or 1,000 times more productive. You cannot make this using the same tools that you used to make games 5 or 10 years ago. I'm from Chicago. So imagine you're trying to recreate the entire city of Chicago to create the game of Watch Dogs, down to the empty soda can on the ground. You cannot do this by hand. You cannot do this using the tools we used to make video games a long time ago. And in every generation, the video games industry figures out how to make its artists and designers an order of magnitude more productive. Going from drawing pixels to robust tools that let artists model from virtual clay. But even that's not enough. We can't model an entire city out of clay. That takes too long. For this, you need procedural tools, where we use math modeled off the results of the previous generation of tools to create complex variations and automatically place elements in a scene. So an artist can just draw a street and it'll fill in the buildings all around it. And this is what in the video games industry we are using to train the next generation of tools, which are GenAI based. And this is what we're using for the next generation of video games. This lesson, however, of using procedurally generated content to train AI systems, highly relevant in healthcare. I'll show you why. So in the last generation, we perfected what we call procedural content generation. So an artist can literally just drag lines to create a building or create a city. So now an artist can basically just, in this scene, they can just grab that mountain or that island and just move it, and the math is going to fill in all the underlying details. This is the expectation of every artist in the video games industry. Any manual work that you were doing 5 years ago is going to be replaced. It's going to be automated. You're going to continually move up the stack. If you're doing the same thing today you were doing 5 years ago, you're doing something wrong. And at level X, we're using some of these same mathematical procedural techniques to create content to train doctors. In this example, we create a mathematical model of plaque psoriasis that allows an artist, guided by a dermatologist, to simply turn some dials, this is all in real time, and create any variation of the disease. Make the skin cracks deeper, make the region between them look wetter, make it crustier. The imagery just emerges from that model. And we're using this to train doctors' brains how to recognize skin diseases on basically at any severity, on any body part, on skin of any color. We talk about reducing racial biases in AI systems. This is very relevant. And under any lighting environment. None of these images I'm showing you are real. These are all generated mathematically, simulatively, from our engine. This is not AI generated, this is generated through math. And we use the same procedural mathematical techniques to model body movement. Mathematical models that allow an artist to overlay a tremor at any frequency or any amplitude on any body type or any body part to train neurologists how to recognize the subtle differences, let's say, between a Parkinsonian tremor and a tardive dyskinesia tremor. And it is this, the procedurally generated content, that we're using to train our next-gen AI systems. This is an example of AI-generated real-time character animation, trained on procedural simulated data. This is what your video game characters are going to start looking like at the end of this year, beginning of next. Now, of course, we're getting to use these generative AI methods at level X to create better training data to train better doctors. But this idea of using procedural content to train AI systems has much broader implications. We can use the last generation's procedural methods to create synthetic data to create smarter, unbiased AI systems. This is just a video of our gastroenterology game, GastroX. You can download it on your phone, do a colonoscopy here while you're watching, have fun. But because we're procedurally, simulatively generating that image, we know exactly where everything is. We know the position of the camera. We know the physiology. We know the position of the tools, the lights, the anatomy, all of it. And we can use this data to train smarter AI systems, systems that know where you are in the procedure and know exactly what's happening. Just like how in games, we're using the last generation's procedural content to train our AI generative systems, now you can use these same techniques in medicine to train smarter diagnostic and procedural systems. So instead of tagging surgical videos as best we can to generate training data, now you can determine the data that you actually want and then the tags that you want, and you can generate it all procedurally and mathematically, in some cases using video game technology. You can automatically generate what it would look like under X-ray, under ultrasound. We can train smarter, unbiased AI systems that know how to find cancer on skin of any color and interpret ultrasound. Which brings me to the next overlooked, I'll say largely overlooked, R&D application of generative AI. There's this misperception that generative AI's current value in engineering is replacing the engineering grunt work. Call it the manual, simple programming work that you were going to outsource to India anyway. No offense to the contingency from India. This is actually a lot less interesting. Yes, it might happen, but what we found is that GenAI allows you to solve your hardest technical problems in orders of magnitude less time. It's not just about being smarter than the code the human programmers generate, it's being smarter than the human programmers. I apologize in advance, I'm gonna have to skip over a lot of technical detail, happy to go over it later if you wanna ask me over dinner or drinks. Simulating light bouncing around a scene is incredibly computationally intensive, but it's critical for simulating complex materials like skin. So light literally, it bounces inside of skin and comes out at another location. This is why skin looks waxy. This is why when you hold your hand up to a flashlight, it glows. This is why computer animated movies from 20 years ago, the characters look like plastic, but today they look real. This is called subsurface scattering. In movies, we have 6 hours to generate every frame, but in a video game or in a medical simulation, we need to generate 60 frames per second. Now, there are ways that you can do this, that you can pre-compute a lot of this, that allows you to do a realistic simulation with interactive shadows, realistic skin, realistic tissues in real time. But these techniques, actually some of which we developed at Microsoft Research, back when I was at Microsoft a decade or two ago, these techniques are very efficient. They can even run on a phone once you've done all the pre-simulation, but the math behind it is incredibly complex. One approach is called pre-computed radiance transfer with spherical harmonics. I'm really giving the translators in the back, making them work hard. The math behind this technique is actually shared with quantum mechanics. Again, happy to delve into it later. And at Level X, we wanted to integrate this rendering, this graphics technique, into our games. But I estimated to do this would be 4 to 6 months of work if we could get it working at all. With ChatGPT, I was able to do it in a weekend. Let me show you what that looked like. Hey, ChatGPT, write code to rotate a 6th-order spherical harmonic vector. ChatGPT goes, well, to rotate a 2nd-order spherical harmonic vector is easy, but a 6th order, well, that's a complex task that requires a deep understanding of spherical harmonics. All right, ChatGPT, just do it. Okay. Well, fine, here's the math, but we need to figure out the Wigner D matrix for that. That's incredibly complicated. All right, ChatGPT, look, you've got a Mathematica plugin, figure out all the math. The engineers in the room are liking this. Use the Mathematica plugin. Boom. In a single weekend, a matter of hours, the whole system is up and running with all the complex math running on real patient data. Next weekend, we're sitting down with the same systems, developing novel methods for simulating bone drilling that runs on a cellular phone. So this is what's interesting. Don't just think about it in terms of what is the grunt work that we can hand off to ChatGPT, but open up, what are the hard technical problems? The ones that you thought would take 6 months to a year to solve, if you could solve them at all. Open up that archive of old problems, because there's a new tool set in town that has a pretty good chance it may be able to solve it, especially if teamed up with your best engineers. And so at Level X, we use ChatGPT and these other systems to generate tons of training content for doctors. It's incredibly helpful. We can create all sorts of combinatorics. We can generate any possible scenario. We can generate all the test results. The results are mind-blowing. Sometimes a little bit too mind-blowing. And herein lies one of the major problems with ChatGPT. ChatGPT, can you come up with a multiple choice question that combines cultural references with dermatology knowledge that a dermatologist would find intriguing and challenging? What's the answer? Sure, here's a question. Which iconic singer was known for their distinctive mole on their face, which was actually a type of benign tumor called a neurofibroma? Marilyn Monroe, Cher, Madonna. The answer is Cher. She's known on this for this mole, which is actually a type of benign tumor called a neurofibroma. Wow. This is interesting, fun. Here's the problem. Everything in red is medically inaccurate. Why? Because ChatGPT is optimized for believability over accuracy. And you need to make sure, this is important from a regulatory perspective, that your editors know that what they are reviewing is AI generated. Because ChatGPT will generate content that a human writer would never say with confidence if they were unsure of the material. A human, when they are unsure about something, will write with less detail. An AI, when it's not sure about something, will write in more detail, and it will make it up. And so one of the things that we find is the same peer review methods that we use with all of our other content to review medical content works with AI-generated content, but with one exception. The editor must be aware that the content is AI-generated, because if they are not, they will make certain assumptions about how humans create things, humans with good intentions create things, and they will miss. And that is why it is crucial that they understand it's AI-generated. Where there is a lot of detail is where you need to look with more depth. It will literally make up references. And this is the bigger problem. And like I said, these systems, again, were not designed for medical accuracy. The people that reviewed and gave feedback to ChatGPT could tell ChatGPT, right in the early versions, whether content it was creating was believable or not. It couldn't tell ChatGPT whether the content that it was creating was accurate, medically accurate enough. And this is why, as we saw earlier, precise control over the input data set is so important. All right, this is, I think, probably my most important example. This is by far the most immediate and I think one of the most important applications of generative AI in healthcare. And that is that I am proud to finally announce the death of cheesy medical stock photography. So you know the problem, right? You open up every website you go to, it's the same smiling actor in a white coat, usually holding a stethoscope wrong. The image to the left, he's a dermatologist. The image on the right is a colorectal surgeon. Yeah, enough. There's no excuse for this anymore. All you folks from industry, if I see these actors again, no. Because now, with generative AI, you can generate any doctor of any specialty doing anything you want in any visual style. No more actors. This, if nothing, this is one of the most important applications of generative AI in healthcare. Let's go talk about one more example. As you start looking at what it means when we start combining these systems, right? The ability to create ultra-realistic characters, the ability to have conversations with digital entities, it opens up a whole array of solutions and things that we probably hadn't considered. And I think one of the interesting applications of GenAI is going to be addressing social problems. Like in the United States, there's a epidemic of human loneliness, and probably the rest of the world too, that is broadly known to have an adverse effect on health outcomes. And if you think about it, right, that elderly woman who has trouble speaking, has trouble remembering things, it's hard to find somebody that's willing to spend time to sit down with her and have conversations with her and engage her and listen to the stories that she wants to tell about her grandchildren over and over and over again. But with the technologies of today, there's no reason you couldn't create a character where she could have pick her favorite, take Humphrey Bogart playing her favorite character from any movie, and the virtual version of that could be created that is filled in with all their information and all of their knowledge about their background. Take visual AI technologies, take LLMs to create a companion that is happy to engage this woman and wants nothing more out of its existence than to talk to her and engage with her about her life and hear all of those stories. And it has the patience to wait and listen to her speak. And I think this is an opportunity to, for example, solve lots of problems that we're not thinking about with AI. It's not just about, replacing the engineering grunt work or necessarily, solving spherical harmonics, but there are opportunities to use these technologies today. There's nothing preventing us from doing this, right? To create systems that can address other fundamental human needs. I'd like to thank everyone for having me here. I'd like to thank the FDA especially for keeping me and my family healthy for my whole life. This is an interesting lesson on how, when you're struggling to think about solutions, in this case regulatory solutions, in your own industry, it's important to look at other industries for inspiration. At Level X, we're always looking at ways to use video game technology, video game design, to accelerate the adoption curve in healthcare, whether that's new AI techniques, new devices, new pharmaceuticals, and new ways to train doctors. And so feel free, that's me. You can feel free to follow me. I continually post about interesting anecdotes and interesting ideas, concepts, progress at the intersection of video games and medicine. Thank you very much.
Thank you, Dr. Fakuria, and thank you, everyone on the organizing committee, our hosts. It's a tremendous conference. If you look through the program, as mentioned, I'm the Chief Technology Officer for Amgen, one of the world's leading biotechnology companies. I was recently the head of research and development for many years, moved over to become our first Chief Technology Officer. And I'm going to give you a framework today that we use to think about the use of artificial intelligence and machine learning in drug discovery and drug development. This phrase, the Hinge moment, is a phrase I started using with our senior staff and our board of directors 5 or 6 years ago. This notion that tech and biotech are now unifying. They are coming together, and it will qualitatively change how we do drug discovery and drug development. Now, before I move on in my talk, I have to tell you a personal story. This venue is very, very special to me. My wife is Korean American, and when we were married many years ago, after some months, a few days after we got married, I started my medical internship. So it was a little while until we had a vacation, and we came on our Korean honeymoon, and we stayed at the Shilla Hotel here in Seoul. And so this is a homecoming of sorts for me. That is quite a nice memory. Physicists for many years have been talking about a grand unified theory, something that would unite what's called the Standard Model with Einstein's theory of gravity. I would posit that we're actually at the moment of unification in drug discovery and drug development when biotech and tech are coming together. And that is being powered by, I think, 3 big concepts. 1, data. We've heard about that already. I'll return to this notion in a moment. 2, extraordinarily powerful experimental methods. A simple example is single-cell sequencing. We couldn't really even do that at scale 5 years ago. Now we do this routinely in an automated, high-throughput fashion at massive scale, generating huge amounts of data. And then finally, we have a revolution in analytic methods allowing us to actually make sense of all of these data. The challenge of enormous amounts of data is that one can find all sorts of correlations. What I always tell my teams, of course, is that I want to know which of them are true, which of them are giving us real insights into disease biology, pathogenesis, response to treatment, and a host of other things. Now, data is the fuel of the 21st century. There's no question about that. How much data are we actually talking about? Well, it's estimated that last year, globally, there were 120 zettabytes of data produced. A zettabyte is a 1 followed by 21 zeros. That is an enormous amount. It's something that the human mind, human psychology, actually can't quite understand, and it is going up dramatically year on year. Why am I bringing this up in the context of our conference? Well, about 30% of all of that data was from the healthcare industry. So it represents an enormous fraction of that 120 zettabytes of data. The question is, can we capture that? Can we ingest it? And can we use it to actually develop therapies that really conquer some of the most serious diseases that we face? Well, one of the key features of that data that I'm describing is now largely human data. Of course, we still use animal models, but most of the data that we're now talking about are human data. Advances in computational biology, in silico protein structure. When DeepMind deposited AlphaFold into the public domain, literally within hours, we began using it. We've now developed an internal program that we call Amgen Fold that actually uses multiple models. And so our bench scientists literally have, with the click of a mouse, the ability to generate in silico protein structures as they're thinking about drug design. I'll talk about large-scale multiomics in just a moment. I think this is one of the most powerful methods we have to actually understand disease phenotypes at a much more fundamental level. And then you heard Dr. Califf mention real-world data and real-world evidence. It is an absolute tsunami of real-world data and real-world evidence that is coming at us. We published a paper a few months ago where we looked at 500,000 individuals by capturing claims and electronic health records data. It was really a landmark in the field in many ways. That's something that we couldn't do 5 or 8 years ago because the computational techniques, simply the storage, wasn't available. "12 years ago, we acquired a company called Decode Genetics, which was founded in Iceland, one of the world's leading genetics centers. And over the ensuing decade plus, we have made Decode our study of human diversity. The reason to study diversity on a molecular level is to gain insight into disease that allows us to then launch drug discovery and drug development programs. Now, when we acquired Decode, they had done several thousand whole genomes. They had genotyped a fraction of the Icelandic population as well as other populations. If you fast forward 12 years, we now have many hundreds of thousands of whole genomes. And in fact, we can do about 20,000 per month. So a decade ago, we had 4,000 in total. Now we can do 20,000 per month. Generating those is no longer rate limiting. It's actually understanding the data that is rate limiting. That is coupled with proteomic data on hundreds of thousands, transcriptomic data, the record of which genes are turned on and off at any given moment, on tens of thousands, and then crucially, dense phenotypic data. Everything from hair color, blood pressure, imaging studies, 10,000 traits, now on close to 3 million individuals. And the purpose is to try to mine these data for insights into human disease biology. Now, you need new analytic techniques to do that. We've heard Moore's law mentioned multiple times already, the notion that roughly every 2 years, the number of transistors on a chip would double, i.e. computational power would double, or the price would be cut in half, depending on how you look at the question. Well, I believe we have now fractured Moore's law. We've entered a period of discontinuity with the rise of artificial intelligence. The models that we're now using in our laboratories improve about tenfold, 1 log every 6 months. So if Moore's law gives you a doubling every 2 years, that kind of change gives you a 10,000-fold improvement every 2 years. As a company spending $5 billion a year on research and development, we have to get our heads around that and say, how do we then take advantage of that technology to create new drugs? Now, you've heard that generative AI has arisen. All of us, of course, have to mention AlphaGo, March 2016. Game 2, move 37. AlphaGo made a move that was later calculated would have been done less than 1 in 10,000 times by a human player, probably less than 1 in 100,000 times. It basically exhibited creativity. That was the moment that I sat up and said, we just saw the future. We just saw the future, and that is going to come to drug discovery and drug development. There was a before and after Monemt. And at that time, we immediately started thinking about how we were going to incorporate this into our research programs. We are now using it across the drug discovery and drug development spectrum, everything from understanding disease, through molecular engineering, through clinical trials, ultimately post-marketing. One can imagine that, of course, pharmacovigilance, safety monitoring will be greatly enhanced with the use of artificial intelligence for signal detection. That is coming very rapidly. So let me give you in the remainder of my talk some examples of how we're doing this to bring it to life. It is no longer theory. The theory has been translated into pragmatic outcomes. Let me start with what we might call precision medicine. One of the challenges when you have a data set like we have in Iceland, which now comprises more than 200 petabytes of multi-omic data, is that it is multimodal. Everything from the phenotypic data, genetic data, proteomic data, imaging data. There may be data from electronic health records. How do you actually integrate that to generate insights into disease biology? And we've now begun building models that allow us to do that. In fact, what we're trying to do is generate a catalog of specific disease phenotypes. We've got several hundred of these now. Some of them match the textbook descriptions of diseases, and some of them are actually different. I think we will actually redefine disease on a molecular level with these techniques as we go forward. It is a certainty. There are certain diseases in the autoimmune space, for example. Think about a disease that's as heterogeneous as lupus. Some patients have skin involvement primarily. Others have severe kidney involvement. Well, we know many tumors can be precisely classified on a molecular level based on their mutational profile. Breast cancer, lymphoma can be discretely categorized into very specific subtypes. The same is certainly true for many autoimmune diseases. We just don't know what those are at a molecular level, and that's why we struggle so much in drug development in these areas, because we don't have an understanding of the basic disease biology. You have hundreds of elements in the immune system interacting, and they're not on-off like tumor genes. They're in fact rheostats that are dialed up and down in a very complex fashion. So it's only through this sort of multimodal analysis using artificial intelligence that I think we'll be able to understand these diseases. Now here's a very simple example. One of the things that we're interested in is development of drugs for atherosclerotic cardiovascular disease, still the leading cause of death globally, and will be for many decades to come. We have ways to predict who's at risk of atherosclerotic cardiovascular disease. Standard clinical risk scores, your age, your sex, your blood pressure, your LDL cholesterol level. More recently, polygenic risk scores have been developed that enhance your ability to predict who's at high risk of events. But all of those are relatively static, meaning you take measurements and they predict a person's risk over the next 10 years. One thing that we were interested in is, can you actually get a more kinetic measure and pick out individuals who are at very high risk, say in the next year or two? And so we did large-scale proteomics to develop what we call a proteomic risk score, and showed that you can actually, in the top quartile of individuals, they are at a 2.25-fold increased risk in these already high-risk individuals of having an event in the near term. These data were generated on large outcome studies that we had already performed in the context of a drug development program. The next step, of course, is validating it prospectively going forward. But this is for sure the future of medicine. This is for sure the future of medicine. imagine you're a doctor and you can now tell someone, well, not only do we know that you have heart disease or a high risk, but we know in the next 2 years you're at very high risk of a serious event. We need to intervene now. That really will change how we conceptualize the public health approach to many of these diseases. Now, of course, Amgen has a almost 45-year history of developing protein therapeutics. We were one of the first few companies to start this industry, and we devote much of our time to that. Several years ago, we launched a program that we call Biologics Next that had the very specific goal of combining wet labs with dry labs. In other words, uniting in silico drug design with the experimentation that we do in laboratories to generate or to enhance molecular engineering. Now, traditionally, finding a drug candidate has often been called, finding a needle in a haystack. We take a large group of candidate molecules. If it's small molecules, we take a chemical library and we screen that, and eventually we get something that's close to what we want, and then we refine that through iterative cycles in the laboratory. With generative AI, we want to start with in silico design of what we want up front, generate candidate molecules, and then very quickly, through a much reduced number of cycles of experimentation in the laboratory, arrive at the clinical candidate. Can we do that? Absolutely. Here's a simple example. Certain side chains will exist on protein therapeutics, and they're bad actors for various reasons. What we were able to do is generate a machine learning model that incorporated huge amounts of the data that we had generated over time, coupled with an automated high-throughput screening methodology to basically predict the characteristics and the type of molecule that you want on the other end. We now know that we can greatly reduce the throughput time, dramatically reduce the throughput time, up to 70 or 80%, and improve the success rate by a 2 to 3-fold measure. For us, that's an enormous improvement in efficiency. In clinical trials, the single largest item in the budget of a head of research and development is the large-scale clinical trials that we conduct, and they are notoriously inefficient. How can we, and we've done them the same way for decades, how can we improve that? Well, we developed a machine learning model that takes hundreds of factors to predict which sites will be most likely to enroll. And what we were able to show is that using this model, the best predicted sites enroll about 2.5 times more patients than those sites selected through traditional means. In that world, that is an enormous gain in efficiency, and it means drugs getting to patients with serious diseases much sooner. And then finally, for this audience, of course, regulatory authoring. Can we actually generate regulatory submissions using artificial intelligence? Well, it's coming. You need to get ready for it, and we need to make sure that we are doing the right thing. So what we did was generate a prototype for the CMC module, module 3 of an FDA filing. Typical module, CMC module is about 1,000 pages, and there is a quality summary that is generated at the end of that that's about 20 pages. And it takes a number of people working for a few months to generate that quality summary. Well, we generated, using a large language model, an algorithm that now will generate the first draft of that quality summary in about 4 minutes. The first one was okay. The second one was really good, and within a year, they will be really, really good. Now, the human has to be in the loop. To Sam's point, the human then has to check. But you can actually generate the model so that it focuses on accuracy, not believability. In fact, it doesn't permit hallucination. And that is the future. So the moment of unification is here. I look forward to the rest of the conference and want to thank all of you for your attention. 감사합니다.
Thank you so much for having me. It's wonderful to be here in Korea and also for such an important set of topics, right? I think AI is developing so fast that I think you'll find a big theme of this conference and also a big theme of this presentation is cooperation, communication, and collaboration, right? We can only get this right by working together. So my topic's going to be on AI and ML-enabled medical devices, so some of the further challenges that generative AI poses. I'm also going to reflect upon some of the challenges with the previous generation of AI, discriminative AI, that we've actually started to address and some of the success stories that we've had. So I'm Johan. A bit about me very quickly. So I'm Global Head of Digital Health Innovation Policy at Roche. So it's basically my job to think about how to regulate digital health, including AI, including generative AI as well. But previously I was Head of Software and AI at the MHRA, so I was regulating software as a medical device for the UK and worked very closely with the US FDA and Health Canada on writing good machine learning practice principles, which are hopefully going through the IMDRF process, the International Medical Device Regulation process, now as a document. And that'll be super exciting to see. But I'm also an honorary associate professor at the University of Birmingham. You'll hear from Alistair Denniston, I think, tomorrow on transparency, also from the University of Birmingham, and also a bi-fellow at Cambridge as well. So here's what we're going to go through. So I'm going to ask a question about what happened to the AI revolution, because we've not really precisely had it yet. It's kind of underway, but we haven't realized all the benefits of getting AI to the clinic, AI to patients quite yet. And then I'm going to consider 3 key challenges that discriminative AI posed that I think we've started to address. And then I'm going to consider further challenges, 3 of them that generative AI poses over and above discriminative AI. And then I'm going to consider what needs to be done. A spoiler, if you want to leave, what I'm going to say is we're going to require more coordination, more cooperation, sooner, better, faster. So if you're going to find this presentation boring, you've already got a conclusion, you're welcome to walk out the door quickly. So digital health is more important than ever, right? So advances such as generative AI are really challenges that only international cooperation can hold, or rather solve. I know this being a regulator last year. I didn't have all the pieces of the puzzle. No one does, so we need to put the pieces of the puzzle together to get some of these challenges sorted. But it's really extremely encouraging to see the MFDS and the US FDA cooperate. It's music to the ears of industry for people such as myself and companies like Roche. We know that we advocate for robust regulation because patients and clinicians need to trust our products. And a big part of that trust of products is faith in the regulatory system and faith that regulators are going to get the regulation right and hold those products to a high bar. That's why we work with partners, regulatory partners and international fora to get this right. So really only together can we effectively protect patients and ensure innovative access to medical devices. But what happened to the AI revolution? So AI did promise, I remember back in 2017 reading papers, it's going to transform clinical pathways. We don't need radiologists anymore. Get rid of dermatologists, stop training as them. But still, we have lots of radiologists. AI hasn't fully intervened, although it has made it to the clinic. But what happened? Well, that promise of revolution is yet to come to pass. I think there are small revolutions sparking. But AI has made it to clinical practice, but that transformative change that we were promised has been stymied by a few things. For instance, difficulties with assuring those models, a lack of access, a lack of acceptance in medical practice, for example, and even basic blockers such as a failure to digitize services. So for instance, Roche are big in digital pathology. The one thing you definitely need to do if you want to use AI in digital pathology is you need to digitize your pathology service, right? But many pathology services haven't digitized. We're a part of that at Roche. We sell the scanners, for example, to digitize your pathology service, but we're not going to get the benefits of AI until we solve some of these infrastructure problems, the infrastructure problems of digitizing services, standardizing data, getting access to data. It's those really boring things that actually unlock the potential of AI going forward. So here's 3 key challenges posed by discriminative AI that we've started to address as a regulatory community together. I'm only really going to focus on one of them, though. But first, what's special about AI with respect to medical devices? Why should you care about it any more or less than regular software? Well, my favorite definition of machine learning in particular comes from a person called Chul. This definition really emphasizes that machine learning systems are trained rather than explicitly programmed. So as you can see on those kind of basic diagrams there, you have rules and data, you put it into a classical programming kind of paradigm and you get your answers, but machine learning flips that on the head, right? It's the training that's important. You put the data and the answers in, it maps it together, and then you get the rules. So instead of us humans inferring what the rules are, the data infers the rule for us. Of course, there is human expert decision-making used in curating that and training it, but that's really the basic difference. And that kind of led to 3 key issues in medical device regulation. So the first one there is robustness, so the ability to maintain performance across intended populations and deployment locations and demonstrate that. I'm going to talk about that in a second, but also the interpretability of AI, right? AI can surprise us. It doesn't necessarily tell us what we think it's going to say. It doesn't necessarily act in the ways that we would usually expect. And so human interpretability, some of these models, you don't necessarily know exactly how they came to the conclusion that they did. And that could be a problem for the safety and effectiveness of those devices, demonstrating the safety and effectiveness of those devices. So that's a challenge. Also adaptivity as well. So I think on Wednesday you're going to hear from a colleague of mine, Cassie Shearer, right, on predetermined change control plans. Adaptivity, one of the key challenges that medical devices and AI pose is that they change fast. So you can retrain them fast. The performance characteristics of those devices can really change day to day, minute to minute, second to second, even if you want them to. So we need new paradigms to manage that change. The current process is not good enough. The kind of months or years that you have to go for resubmission just does not work. It is a key safety priority that we be able to update these devices to maintain performance across time. So here's just one that I'm going to dive into, the robustness problem for AI. We've made some really good advances as a community in starting to address this problem to make sure AI is safe and effective for patients, and we can demonstrate as much. So for instance, for robustness, we've had better understanding of what drives data variation. We have better understanding of what representative data means. If you see Alistair Dennison in a corridor, ask him about a project called Standing Together, which is a standard for data diversity for AI used in healthcare, a really important standard. We now know we have a better understanding of what diversity means and what's important for the safety of these devices. We also have better testing methodologies to signal robustness of models as well. So we're in a much better circumstance for robustness than we were, say, back in 2017, 2018. But also interpretability as well. So we have a better understanding of what the clinical community actually wants, including transparency. So usually the clinical community doesn't really want explainability of models. They actually want just basic facts about the model. What was the training set? What was the test set? And does that look like my patient, right? And patients even want something even more basic. Often they want to only trust their clinician, or they want some even more basic facts about the model. We also have better understanding of what is technically feasible and explainable AI methods as well that we can deploy. And also we're progressing methodologies to analyze the usability of AI with a medical purpose as well. So again, huge advances, and there's some fantastic standardization work that's going on as well. You'll hear from Pat, and I think in the next few days, who's basically the kind of standardization guru as well. So I'd say if you see Pat, corner him and ask him about these standards under development as well. Adaptivity as well. So we now have better understanding of what drives data drift, or I think it's still developing. So when we have to update those models, when they've now gone below a threshold that would be acceptable. And also we have crystallization of predetermined change control plans to assure those modifications. That's a much better paradigm for assuring change. With medical devices, we can't have unconstrained change, right? We still need a procedure to make sure the change is managed, to make sure the change improves the device, that it helps rather than hinders. And I think PCCPs, predetermined change control plans, are a big part of that future. So I think what this means altogether really is that as a community of regulators, industry, and academia, actually we've started to really push the state-of-the-art forward. We now know what good looks like, or rather we know what better looks like for AI as a medical device for discriminative AI. So I think these successes are actually something to celebrate, there's something to learn from, and there's something to drive forward, because There are further challenges posed by generative AI. We now have a whole new generation of AI. That document that I referenced earlier, Good Machine Learning Practice Principles, it's not fully fit for purpose, I'd say, for this new generation. There are some tweaks required, some further thinking that we need to develop. So here's some further thoughts, 3 extra challenges that I think this new generation poses. We're going to have to, again, get to grips with them as a regulatory community. I think the really scary thing for me is the speed of this, right? I mean, this literally, really kicked off properly last year. So I think the only thing that keeps me awake at night, really, or not the only thing, one of the things that keeps me awake at night is what's going to happen this year, what's going to happen next year, because we're already behind. So roughly, here's what I mean by generative AI in this context. So GenAI is just the use of AI to create new content like text, images, music, video, and so on. But really, it's powered by foundation models, right? So that's the new paradigm of deep learning that utilizes transfer learning. And really, I think you kind of get the power of that with 2 things together. So transfer learning is what makes foundation models possible, but scale is what makes them powerful. So that's kind of what we're talking about in this context. And there's 3 key challenges that I think it poses. So the first one that I'll talk about last is kind of robustness squared. If you're a mathematician, I think that use of squared will immediately offend you because it's completely incorrect. But nevertheless, it's robustness on kind of a next level robustness problem that we're going to have to solve. There's also software as a medical device qualification. So what counts as software as a medical device in this context is going to be further challenges that generative AI pose. And there's the problem of SOUP. For those that don't know the acronym, that's software of unknown provenance. I think we're also going to have issues of documentation, how we documentate those models. I'm going to go through these 3 challenges briefly now. So here's software as a medical device qualification. So it's a really important question, it's a really important problem in regulation that you know what's regulated. That's important for industry because that means you have clarity about what standard you need to meet and when you need to meet it. But it's also important for regulators as well because you'll spend half your time as a regulator saying what is and what is not regulated. But really it's characteristic of foundation models that they use transfer learning. So they fine-tune often another model, for instance, for a medical purpose to make it useful for a medical context or a medical purpose. So there are really kind of 2 sub-challenges for qualification here. So some of the big foundation models, for example, if they don't exclude a medical context, if they don't exclude a medical purpose, they themselves might be a medical device. But here's the more likely problem. It is much more common to fine-tune those base foundation models for a more specific task, and then you create a fine-tuned model. But what part of that fine-tuned model is a medical device? Is it just that fine-tuned model in and of itself? Is it the foundation model? How do you get the documentation of those 2 models together to assure both of them, or maybe just one of them, for example? That is the problem of SOUP. So here's the problem of SOUP. So as noted, it is common in healthcare to fine-tune a base foundation model for a more specific task, although there are some foundation models built for medicine in particular. But that creates an opportunity to harness those more powerful models for more specific tasks. So it allows us to use that kind of large body of knowledge to fine-tune it for a medical purpose and have the best of both worlds. But that also creates challenges, though. So for example, often the developer of the fine-tuned model will not have documentation for that foundation model. It is key to proving the safety and effectiveness of software as a medical device that you do have documentation over that model. So it's likely that software of unknown provenance is at the heart of software as a medical device if you fine-tune it for a medical purpose. I kind of call this black hole soup to distinguish it. So we're used to having soup in medical devices. We're used to having software of unknown provenance. Basically, all medical devices, software as a medical device, will have soup in them somewhere. But having a foundation model at the base of your device is black hole soup. It is soup of massive quantity, and also it potentially has consequences if you don't have documentation over it. And that means it's really difficult to deploy probably sufficient controls for risk management purposes if you have that much soup in your model. It is black hole, chunky soup, if you want another term. Even if the fine-tuned developer has access to documentation, though, we still likely don't have the state of the art to fully understand how to analyze the performance of those models as well. This is the next challenge that I'll talk about, robustness. So let's suppose you know what software as a medical device is. Let's suppose you know exactly what part of your GenAI model, foundation model, whatever, is a medical device. Let's suppose you have all the documentation that one could possibly have over that model. Well, we're still left with this problem. So there are likely challenges with respect to how we measure the performance, the methods we use to test robustness, and how we characterize errors in generative AI. So for instance, just 2 examples here. So consider the problem of sample sizes with respect to functional testing. So functional testing is one of the major ways that you test software. You basically push inputs in, and you get outputs, and you compare the two, seeing whether what you got is what you expected. But functional testing, given that it is common to have a lack of constraints in terms of function inputs and outputs, the sample size to provide an actual adequate assurance model quickly balloons, right? With some of these foundation models, you can input any given input and you can get any given output. It is very difficult to test them in the ways we'd usually expect for software as a medical device. But also, in addition, I think what's an even harder problem is how you detect errors, how you detect hallucinations in the model. Really, the state of the art in how to measure error in these models is not yet settled. People are developing methodologies. I've seen many papers, but none of these papers really agree with one another, right? So that means we don't actually know how to characterize the performance of generative AI. And that concerns me when it comes to using generative AI for a medical purpose, because we need to know how to measure the performance of these devices before we deploy them for safety-critical purposes. So really, I think there's a lack of consensus at the moment on how to detect and characterize error in these models. But I think this is not necessarily something to be down about. I think what it requires is all of us to come together to develop that data science. This is a core problem of data science that we have to go through as a community, as a set of regulators, as industry, even as patients together, right, to overcome it. So it's overcomable. I just don't think we're there yet. So really, I think there's a hierarchy of challenges here, right? The software as a medical device qualification problem. Actually, that's a known challenge, which is just further amplified in the context of GenAI. But it's likely solvable just via clear guidance. Actually, I think there's an easy route to solving that problem. With the soup problem, well, that's a known challenge, but it's really a step change to black hole soup. So solutions are going to require probably disclosure of foundation model documentation or new methods to constrain and control risk in those kind of models. But still, it looks quite solvable. But robustness, though, is a fundamental challenge to the methods and state-of-the-art for how we measure the performance of software as a medical device. It's likely going to require fundamental problems of data science to be solved on the generative AI side, but also software as a medical device regulation to shift, to be flexible, to meet those challenges as well. But really, those solutions are yet to crystallize, or they're currently out of reach. So we need to do more to reach them. So really, the rise of generative AI, look, it requires cooperation across the international community of regulators, academia, clinicians, and industry, and even more. The good news, though, is that some of this cooperation is already happening, right? Today, tomorrow, and Wednesday is evidence of some of that cooperation, but also you can see it at the IMDRF, the International Medical Device Regulators Forum as well. The AIML-enabled subgroup is one that I co-chair with the MHRA. We're already starting to consider the position of generative AI with respect to that guidance. And also, just to give a quick shout out to Korea MFDS as well. Korea MFDS actually founded the home working group of that, the AI working group at the IMDRF as well. So congratulations for that forward thinking as well. So this is the tagline for Roche, which I think is the best tagline of any company here today, which is doing now what patients need next. So we're here to be a trusted partner to regulators and the rest of the community to make sure we solve these challenges going forward to ensure patients are served. And I think I have stopped just on the dot, or maybe 4 seconds over.